Hello, my name is Anthony Scott, and along with my partner Storm Stokes, we are presenting our AI801 final project. Today, we're going to dive deeply into the mathematics of partial observability. We'll walk you through the theoretical limits of constraint satisfaction, the 5 custom AI architectures we engineered from scratch, and the empirical data from our 5,000 game automated benchmark. This project goes far beyond writing a script to beat a game. It explores a fundamental question in artificial intelligence. How do we mathematically force a machine to make the safest possible decision when its sensors are lying to it or when the data is fundamentally incomplete? I'll now pass it over to Storm to explain why we chose this specific environment, Minesweeper.
Thank you, Anthony. To understand the academic value of this project, we have to look past the fact that Minesweeper is a retro computer game. In the realm of artificial intelligence, this environment is perfectly classified as a partially observable Markov decision process. In real-world robotics, machines never have a perfect omniscient view of their environment. If you have an anonymous rover navigating a disaster zone, or an industrial SCADA system managing a factory floor, sensors fail, cameras get occluded by dust, LiDAR signals drop out. The AI must infer the hidden state of the world to prevent a catastrophic failure. Minesweeper perfectly isolates this exact mathematical constraint. The AI is completely blind to the state of the board. It only receives localized integer-based feedback. And our core challenge was, how do you program an agent to make a guaranteed safe move when it only has a fraction of the truth? When a board is relatively empty, let's say a 10% mine density, finding a safe move is trivial. The logic chains are short and easily resolved. But as mine density increases, the environment enters what complexity theorists call a mathematical phase transition. Much like water freezing into ice, the structural nature of the problem suddenly changes. The numerical clues become highly coupled, creating a massive interconnected boundary of unknown cells. We refer to this boundary as the fringe. Once the board hits about 20% density, simple logic chains completely break down. The board states overlap, and finding a safe move transitions from a simple deduction into a computationally explosive problem. Anthony will now explain the theoretical limits of this phase transition and why it breaks standard algorithms.
The breakdown Storm just mentioned isn't a programming issue. It is a proven mathematical wall. In the year 2000, mathematician Richard Kay published a paper proving that Minesweeper is NP complete. He demonstrated that you can actually build functional Boolean logic gates like AND, OR, and NOT gates using specific configurations of unrevealed mines. Because you can build a logic circuit out of this, Minesweeper is computationally equivalent to the Boolean satisfaction problem. Building on this, the MIT hardness group recently proved that with a specific task of inference, which means mathematically proving that a single covered cell is definitely safe, is CO NP complete. Now, what does this mean for our AI? It means that there are no fast mathematical shortcuts, which is the fun part of the project. Now, to calculate the exact probability of a mine on a connected fringe of just 30 cells, the AI must evaluate an exponential search space of O to the n. For 30 cells, that's over 1 billion possible board realities. The AI has to check every single one of those billion realities against the board's constraints to see if they are mathematically valid. It is intractable. If we force a standard algorithm to do this, it'll run out of memory, exceed maximum recursion depths, or simply crash the program. We have to build architectures that could bypass this wall. To test our solutions, we couldn't just use a generic web environment. We built a custom Python and simulation API from scratch to act as our testing ground. To ensure that we could run thousands of tests for statistical accuracy, we had to strip out all of the graphical user interfaces. Rendering graphics using libraries such as tkinter or Pygame takes up massive CPU overhead, which bottlenecks the data collection. Instead, our environment tracks the board internally as a discrete numerical tensor. Covered cells are represented by -2, flags by -3, and clues by positive integers. By vectorizing the board state using NumPy arrays, we allowed the agents to run matrix operations natively and rapidly, executing entire games in fractions of a second.
Before our agents can make a decision, they have to translate that raw tensor data into usable logic. Our agents execute a pre-processing loop that iterates over the numerical clues and converts the physical grid topology into a system of algebraic equations. For instance, if the agent reveals a 1 and that cell touches 3 unrevealed neighbor cells, let's call them cells A, B, and C, the preprocessor generates the equation A plus B plus C equals 1. It knows that exactly one of those variables must be a mine. These linear constraints are instantiated as object-oriented sentences. The collection of these overlapping sentences form the agent's active knowledge base, which is updated dynamically every single turn. Our foundational model is the Baseline CSP. It treats the knowledge base strictly as a system of linear equations. It applies matrix algebra and subset rules to deduce guaranteed safe cells. Let's look at a concrete example of how the AI thinks. If sentence 1 dictates that variables A plus B equals 1, and an overlapping sentence 2 dictates that A plus B plus C equals 2, the agent recognizes that sentence 1 is a strict subset of sentence 2. It algebraically subtracts the cell arrays and the mine counts. 2 minus 1 equals 1, leaving only variable C. The agent deduces immediately that cell C must equal 1, meaning it is a guaranteed mine, and flags it. It iterates this logic recursively, cascading across the board until no further mathematical guarantees can be made.
Because the NP complete wall, the CSP math eventually runs out. The board state becomes entirely ambiguous. When this happens, our baseline CSP uses a hard-coded structural heuristic. It blindly guesses in dark corners of the board. Why do we force it to do this? Well, because the active fringe it was just trying to calculate is inherently dense with mines. Blindly clicking a cell you were just trying to solve is incredibly dangerous. Guessing an untouched corner is a structural attempt to bypass the dense cluster and to find open space. Furthermore, a corner cell only has 3 neighbors, while a center cell has 8. Statistically, clicking a corner minimizes your exposure to surrounding mines. We also built 2 alternative fallback mechanisms. The native CSP uses the exact same logic engine, but when it gets stuck, it calculates a mathematical average of the numerical clues adjacent to each unrevealed cell. It divides the clue value by the number of covered neighbors in order to generate a crude risk score, picking the cell with the lowest average risk. Next, we built the DFS agent. This moves away from the linear algebra and uses a depth-first search. It builds a backtracking binary tree, recursively assigning a 0 or 1 to every cell on the fringe. However, to prevent the algorithm from stalling on that O2 to the n search space, we placed a hard computational limit on it, forcing the search to terminate after discovering 2,000 valid solutions, which it then aggregates to make a choice.
Our fourth model moves past basic logic and into advanced probability. The hybrid Monte Carlo agent uses graph theory to split the overlapping constraint sentences into isolated components or subgraphs. If a component is small, specifically under 18 variables, the agent guarantees a complete truth table. 2 to the power of 18 is roughly 262,000 combinations. The computer can handle that. It tests every possible binary permutation against the CSP rules, throws out any world state that violates a clue, and counts the results of the valid states. This generates a 100% accurate, exact marginal probability matrix for every cell in that specific cluster, allowing the agent to pick the absolute safest mathematical move. But what if the cluster has 40 variables? A truth table is physically impossible. For this, we built our most advanced model, the hybrid MCMC, using simulated annealing. Simulated annealing is an algorithm inspired by metallurgy, where metals are heated to high temperatures and slowly cooled to remove crystalline defects and reach a state of minimum energy. Instead of building the board from scratch, this agent generates a random binary state for the entire fringe. It then calculates an energy score based on the total number of constraint equations that the random state violates. It then iteratively flips single variables, trying to get that energy score down to 0, which represents a perfectly valid rule-abiding board state.
Now, let's look under the hood on how these algorithms are actually implemented in our codebase, starting with the Baseline CSP. Because we treat the board as a system of linear equations, our logic engine relies on set theory. This pseudocode shows our primary inference loop. The agent iteratively compares every sentence in its knowledge base against every other sentence. If variables in sentence 1 are a strict mathematical subset of sentence 2, the algorithm performs a set difference operation on both cell arrays and their associated mining counts. This generates a newly isolated smaller equation. This while loop continues to fire recursively until the length of the knowledge base stabilizes, meaning no further mathematical guarantees can be extracted from the current board state. When that CSP loop fails, the native CSP agent attempts to calculate risk. Here's the mathematical fallback it executes. For every cell currently sitting on the unknown fringe, the agent scans the knowledge base for any sentence containing that cell. It calculates a localized fractional risk by dividing the mine count by the number of variables in that specific equation. It then averages those fractions across all overlapping clues to assign a final float value to that cell, ultimately selecting the cell with the lowest average. We call this native because it makes a dangerous statistical assumption. It assumes that overlapping constraint equations are statistically independent of one another. In a highly dense Minesweeper board, they are deeply dependent, which is why this native averaging fails in complex phase transitions.
Moving to search algorithms, here's the recursive backtracking engine for our depth-first search agent. Instead of linear algebra, this algorithm sequentially assigns a binary 0 or 1 to every variable on the fringe to build a search tree. Notice the for loop at the bottom. It tests 0, which means safe, before it tests 1, which means mine. Now look at the very top of the function. This is the exact line of code that caused the DFS agent to fail our benchmark with a 0% win rate. If length of solutions is greater than 2000, then it returns. Because evaluating an NP complete space is intractable, we had to artificially amputate the search tree to keep the execution times under a fraction of a second. Because it evaluates the 0 branches first and cuts off early, it suffers from extreme search tree bias. To calculate true exact probabilities, our hybrid Monte Carlo agent relies heavily on graph theory. If you have a fringe of 30 cells, calculating 2 to the power of 30 is impossible. But if you map the overlapping equations as edges and nodes, you can run a connected components algorithm to split that massive fringe into independent disconnected subgraphs. This pseudocode shows that optimization, if a subgraph component is successfully isolated to 18 variables or less, the agent leverages Python's intertools library to generate a complete truth table. It tests every single binary permutation, filters out the impossible realities using the check consistent function, and counts the precise fractional occurrence of mines in the surviving valid worlds. It breaks an impossible O2 to the power of n problem into multiple easily solvable O2 to the power of k subproblems.
Finally, here's the mathematical engine for our most complex model, the hybrid MCMC. When a subgraph component exceeds 18 variables, truth tables are impossible. We must use simulated annealing. The algorithm generates a random board state and calculates energy, which is simply the absolute sum of all constrained equation errors. Notice the cooling schedule at the top. The temperature T decays exponentially based on the current step. Look at our else if block at the bottom. This is the Metropolis-Hastings criterion in code. If flipping a variable makes the board worse, meaning the energy goes up, the algorithm uses math.exp to calculate a probability of acceptance because T is the denominator. A high temperature early in the loop forces the AI to accept bad moves, vibrating the state out of the local minima. As T approaches 0, the probability of accepting a bad move approaches 0, effectively pulling the algorithm down into a valid zero energy board state so that we can sample it.
We previously mentioned that our hybrid Monte Carlo agent splits the fringe into isolated components to avoid exponential explosion. I want to emphasize the strict mathematics of why this is necessary. If we have a connected fringe of 30 unknown cells, calculating the exact probability matrix requires 2 to the power of 30 operations, over 1 billion checks. However, if we map the overlapping constraint sentences as edges in an adjacency matrix, we can use a connected components algorithm to identify independent subgraphs. If we prove that those 30 cells actually form two completely disconnected clusters of 15 cells each, the math changes entirely. The complexity drops from 2 to the power of 30 down to 2 to the power of 15. That is a reduction from 1 billion operations down to roughly 65,000 operations. This graph theory implementation is the only reason exact probabilistic inference is possible in real time.
Now, let's look at big O time complexity of our architecture. The baseline CSP operates in O2 to the S time, where S is the number of active sentences in the knowledge base, because it must compare every equation against every other equation to find strict subsets. The DFS agent operates in O to the N time, but we artificially bounded it to a constant K of 2000, turning it into O to the 1 time constant, turning it into O to the 1 constant time operation, but it's at the expense of the search tree bias. Finally, the simulated annealing MCMC agent operates in O m times V time, where m is a fixed number of temperature steps in the cooling schedule, and v is the number of variables it flips. By defining m mathematically up front, we guarantee that the MCMC agent will never hang regardless of how massive or dense the board becomes.
You might be wondering why we specifically chose to test our agents at a 16 by 16 grid with exactly 60 mines. That equates to a 23.4% mine density. This was not a random choice. In the study of Boolean satisfiability problems, or KSAT, there is a critical ratio of constraints to variables. Below this ratio, problems are under-constrained and trivial to solve. Above this ratio, they are over-constrained and quickly proven unsolvable. But exactly at this critical ratio, algorithms experience a massive spike in computational cost because they have to search the deepest parts of the decision tree. For Minesweeper, this phase transition occurs exactly around the 20 to 24% density mark. By forcing our AI to operate strictly at 23.4% density, we maximized the number of ambiguous states, preventing the AI from coasting on simple logic and forcing it to demonstrate its probabilistic engines.
Shifting to the environment API, processing the agent's actions require careful memory management. When an agent clicks a safe cell and that cell is 0, the environment must immediately unmask all adjacent non-mined cells. If those cells are also zeros, the process cascades. We programmed a recursive flood fill algorithm to handle this state aggregation. However, on a 16 by 16 board, a massive cascade of zeros can easily exceed standard stack limits in Python. We had to override the system defaults, adjusting the recursion depth limits natively in the sys module to ensure that the evaluating massive open spaces would not trigger Stack Overflow errors on our high-speed automated benchmarking.
Finally, we had to ensure our benchmarking architecture could scale. Simulating 5,000 independent games requires processing hundreds of thousands of individual board states. If we had tied our simulation to a graphical interface running at 60 frames per second, the rendering overhead would have bottlenecked our data collection by a factor of 100. By decoupling the logic engine from the visualizer and passing memory pointers to our numpy arrays, rather than executing costly deep copies of the board state at every turn, we bypassed thermal throttling on the CPU. This allowed us to execute thousands of head-to-head simulations and gather stable, irrefutable statistical data in a matter of minutes.
Now, let's look under the hood of how the simulated annealing actually works. If flipping a variable reduces the energy score, the algorithm accepts the move immediately. But if flipping the variable increases the energy, making the board more invalid, it doesn't instantly reject this. It uses the Metropolis-Hastings criterion. It calculates the acceptance probability using the equation e to the negative delta e over t, where delta e is the change in energy, and T represents the temperature, which drops over time based on an exponential cooling schedule. Early in this calculation, the temperature is high, meaning the AI will accept bad moves. This acts as a mathematical shakeup, preventing the algorithm from getting trapped in local minima. As the temperature cools, it acts like gravity, pulling the algorithm down into a valid board state. By collecting thousands of these valid samples, we can estimate highly accurate possibilities without ever searching the full space. To test these 5 architectures, we ran a massive automated benchmark. We simulated 1,000 independent games per agent at an expert level density of 23.4% on a 16 by 16 grid. To process these 5,000 total games efficiently, we utilize a low latency terminal visualizer, as shown here, that maps the NumPy arrays directly to ASCII characters, allowing us to observe the agents in real time. Storm will now reveal the quantitative result of this benchmark.
The empirical data directly contradicted our initial hypothesis. Our simple baseline CSP achieved the highest overall win rate at 16.1%, outperforming our highly advanced MCMC model by 1.3%. You can also see the DFS agent completely failed with a 0% win rate across 1,000 attempts. However, when we look at the computation times, we consider the architecture a massive success. The hard-coded fallback limits we programmed into the heavy mathematical agents, like the 2000 solution cap for the DFS and the exponential cooling schedule for the MCMC, successfully prevented any system hangs. All 5 agents operated under 0.02 of a second per game on average.
There are 2 massive academic takeaways from this data. First, why did the DFS agent score 0? Well, it suffered from search tree bias. Because we capped it at 2,000 solutions to maintain that high execution speed, it evaluated the binary 0 branch, the safe branch, first due to lexicographical ordering. Because it hit its computational limit so early in the tree, it never actually reached the 1 or mine branches for its early variables. Therefore, it falsely concluded that those early variables were 100% safe simply because it ran out of time to simulate the alternative realities. This led to highly confident fatal errors, proving that capped search algorithms are highly dangerous in dense environments. The second major takeaway is what we called the density paradox. Why did the simple logic solver beat simulated annealing? Our MCMC model spent all of its computing power finding the statistically safest move inside the active boundary fringe. But at 23.4% density, the fringe is inherently packed with mines. Our MCMC model spent all of its computing power optimizing probabilities inside the active boundary fringe. But at 23.4% density, the fringe is inherently packed with mines. The baseline CSP couldn't do the advanced probability, and when the logic failed, it blindly guessed in the unrevealed dark corners of the board. Statistically, the open unrevealed board had much lower overall mine density than the active fringe. By abandoning the math entirely, the simple agent bypassed the dense clusters and survived for longer. It proves that sometimes a blind structural heuristic is mathematically safer than an optimized probability calculation.
In conclusion, building a robust AI agent requires more than just advanced math. In environments with extreme uncertainty, strategic risk aversion is key. Recognizing exactly when mathematical calculations become computationally dangerous and relying on structural heuristics instead yields higher survival rates in dense environments. For future work, we plan to improve the hybrid MCMC model by implementing a global density check. This algorithm would calculate the risk of the fringe, compare it to the baseline density of the remaining open board, and dynamically force the MCMC agent to abandon the fringe and guess heuristically if the local risk is too high.
Here are the core references that guided our logic models, constraint satisfaction frameworks, and NP completeness proofs. Here is the references continued. Here is our Git repository. I highly encourage everybody watching this video to go check it out. Our report and README markdown files are in there. It is completely standalone, and it will walk you through how to clone the repository and run our models. At this point in the presentation, I would like to switch over to the terminal to show you a demonstration of the agents, how to play Minesweeper yourself, and how to run the benchmark test. So once you go to the Git repository, you can do git clone and then click that code button and then paste it in, and this will be able to get you to clone in. So as you can see here, once you cd into the project directory, we have agents, environment, results, test, and then readme and report. The agents folder holds all of the agents. So this is our baseline CSP, hybrid MC, hybrid MCMC, and the other models. Environment, there are 2 files in there that actually builds the Minesweeper environment to play the game, and also prints out the output for the automated benchmark. We disabled this so that way it could just play the game and not have to redraw the map of Minesweeper every single time to save time and compute power. Results houses the graphs that are created from the tests. As you can see here, the test folder houses the benchmark, generate plots, and test terminal. The test terminal is actually how you can play Minesweeper. The generate plots is the Python code to create the graphs that you saw earlier in the presentation. Benchmark is the automated test that we have where it ran 5,000 games, 1,000 per each agent. And at this moment, I would like to go ahead and run one of the agents just to show you how it works. So we'll go ahead and type in agents, and we'll go ahead and do the baseline CSP. So if you type it in like this and run, and it'll play Minesweeper until it either fails or wins. So as you can see on the last move, it failed. And at this point, it actually won this time. Now we are going to run the benchmark test to show you how that works. So at first is our DFS agent. As you can see, it's very quickly going through these games, and that will not be the case for these other ones because it's very quickly failing on those problems. Up next is our native CSP, I believe, or baseline CSP. As you can see, there's a lot of logic stuck. So that's where it's trying to figure out the equations of the mines around it and getting confused because it can't solve that system because there are multiple configurations. This is another CSP that just finished. Now up next is our hybrid MC agent. This is the Monte Carlo agent. And lastly, our hybrid MCMC agent, which is our Markov Chain Monte Carlo agent. And as you can see, we had very similar results to what we had in the presentation earlier, where the baseline CSP agent actually wins over top of all of the other agents. So just to show you how to play Minesweeper, one of the first things that we realized whenever we built Minesweeper was that whenever you choose your first move, it cannot be a mine. Originally, whenever I created the environment, I had it so that way I placed all the mines first, and then whenever you chose, sometimes your first move might have hit a mine and it killed the game instantly. So to prevent this, I actually went in and made sure that the first move never hits a mine. So we can do 1, 1, 0. So as you can see, once we make the move, the top area where it says has dots, those are just empty spaces that don't have anything. And then we can see that we have near here, there's a mine here because there's 1, 1, and there's no mines around, so it must be here. So that's 3, 2, and then 1. We'll mark it as a mine. And you can see F as a flag, and then you would just continue through here until you're done. If you win, it's an automatic. It'll tell you working, but fun thing happens if you do hit a mine, which there's easily a mine here on 3, 7. If you do this, 0 is for no safe space. 1 is for flag. You can see, boom, you hit a mine, which is right here, and the mines show up as stars. So that is the end of our presentation. Please go check out the Git repository. We spent a lot of time on this. We are very proud of it. So thank you again for listening to this presentation. Go check out the Git repository. Thank you very much.